We are now going to have a look at a very important term which is used when we look at fluid statics, and this is the term fluid density. So what exactly do we mean by that term? What is fluid density? Well, let's say we have the ratio of two materials. And let's say that the ratio of those two materials involve their density. So if we have the density of an object and we divide that object by the density of water, then what we have is the fluid density. So in other words, in calculating the relative density of materials, the water density is usually taken as the standard density, because it is a common material among all the other materials that we're familiar with. So in other words, water is taken as the standard in terms of the density. So when we work out the fluid density, we're essentially just dividing the density of the object or the material by the density of the water. And we can express it in this way. We can say that the relative density is equal to the density of the object divided by the density of the water, and that gives us the relative density. We're now going to have a look at what's called hydraulic machines. And hydraulic systems, they use the principle that the pressure that's transmitted throughout a liquid is actually uniform. Now, this pressure that's transmitted through a liquid is very important when we look at, for example, hydraulic brake systems. But let's have a look at the basics in terms of what hydraulic systems are. So we know that hydraulic systems use pressure, and we know that hydraulic systems use the pressure transmitted throughout a liquid. Now, hydraulic systems are actually used to transfer movement from one part of a machine to another, and it does so without actually linking the parts of the machine mechanically. So in other words, the transfer of movement is done using the principle of pressure. Now, when we examine in a hydraulic system, and we're going to use the diagram below to explain hydraulic systems, we have two pistons, and you can see here that the two pistons are linked together by a tube. And inside of this tube there is a oil, a special type of oil, and we can call this oil the hydraulic fluid. So if you apply a force to the piston here, what will happen? It will apply pressure to the hydraulic fluid, and that hydraulic fluid will apply a uniform pressure throughout the liquid and apply a force to this piston, and as a result of that cause the movement of this piston. So you can see what we mean here when we say that it's the transfer of movement from one part of a machine, from this part of the machine to this part of the machine, without linking the parts mechanically. There's nothing connecting this piston to this piston. The only thing in between these two pistons is the hydraulic fluid. The pressure in all parts of the hydraulic system is the same. So the pressure generated here is the same as the pressure generated here. What is hydraulic lift? Well, hydraulic lift is a hydraulic machine which is used to raise heavy objects, and this is done by applying a small force. And in fact, it's a kind of what we call a force multiplying machine, because what you're basically doing is it's a kind of a lever really in terms of multiplying the force that has been applied initially in order to produce a bigger force in order to lift a very heavy object. And this is the hydraulic press. Well, a hydraulic press is a machine used to shape metals or compress materials into smaller volumes. So in a sense, this is really a compression type machine. And we're going to have a look at some of these a bit later on. But the most important in terms of your studies in physics, in terms of looking at hydraulics, is the application of hydraulics in what's known as an hydraulic brake. And the hydraulic brake is a type of hydraulic machine, and that uses fluids, which, as we saw earlier on in our introduction to hydraulics, the fluid is used to transfer pressure from a pedal to push brake pads onto a brake disc. And this is basically how the braking system works in many automobiles, in many cars and trucks. And this is the one that we're going to be looking at in a lot of detail. So let's have a look at the hydraulic brake and how it works. Well, this is a nice setup that you could actually do at school in your classroom or in a laboratory. So let's have a look at this simplified hydraulic brake system. Now let's imagine this is the hydraulic brake system in a car. How would this work? Well, in a car, the hydraulic system uses a small, what we call master piston, and it uses a bigger slave piston. Now, we're going to have a look at each of these in turn, but if you look at the diagram's labeled to show you the different pistons. Here we have a foot pedal, which would represent the foot pedal in your car. And you can see that as you press down on the foot pedal, that you're pressing down on a syringe, and that syringe you can see has a plunger, so that when you press down on the foot pedal, then the syringe also presses down, and it presses down on the liquid inside the syringe. Now this is called a slave piston. Now if you look at the diagram, you can see that there are quite a few slave pistons. There's one here, and there's also one here. And inside of that slave piston, inside of the syringe, which is acting as the sort of piston in this example, there is a fluid, and that would be the hydraulic fluid. So the master piston is used to apply a force. And this puts the liquid under pressure. So in other words, this slave piston over here really is the master piston. And that's applying the force. And that's putting pressure on the liquid inside of the system here. The liquid's under pressure. And this pressure is then transmitted to the pistons on all four wheels of a car. So if you could imagine this actually operating on all four wheels of a car, then this would be basically what happens in terms of the foot pedal presses down onto the piston, the master piston, and that causes pressure to be transmitted to all of the pistons in the car for all the four wheels. You should be able to see that if we trace our pathway all the way from the foot pedal all the way around to the slave pistons, then you can see that there isn't anything attaching that particular piston to this one here mechanically. The only thing that's in between them is the fluid. There isn't anything mechanically attached to the pistons. So all hydraulic systems use two pistons linked via a pipe which carries a special oil which is called the hydraulic fluid. And again, just to represent this visually, here we can see the force being applied to this piston, and in between the pistons, because this is piston 1, this is piston 2, in between the two pistons we have the hydraulic fluid. Now, all hydraulic brake systems, especially those used in cars, they tend to use a smaller master piston. So over here in the diagram, you can see that this would represent that smaller master piston. And the hydraulic brake systems also use what's called the bigger slave pistons. So over here you can see, in terms of the pistons which are attached to the brake pads, these are larger or bigger slave pistons. So the master piston is used to apply a force. And as you can see here, when the driver presses down on the brake, that then applies a force to the master piston, which then applies a force to the hydraulic fluid. And so that hydraulic fluid is now under pressure. And then that pressure is then transmitted to the pistons of all four wheels of the car, as shown in this diagram for one of those wheels. Now, this is another very useful activity because it sort of gives you an idea of the input force in the hydraulic system and the output force. So here you can see that if the input force is 2 newtons, if we apply a force here of 2 newtons on this piston, what this is showing you is that the force applied against this particular piston is going to be 6 newtons. In other words, it is a force multiplier. You're multiplying the force. In other words, the input force is smaller than the output force. The output force is larger. So let's see what happens if we increase this to say 4. Now you should be able to see that the output force in this relationship is 12. Okay, 3 times as much as the input force. And let's change this now to 5. And let's see what the output force is. It's 15. Again, it's 3 times as much as the input force. So the output force of 15 is 3 times that of the input force. So this is a force multiplier. It multiplies the force. It multiplies the input force 3 times in this particular example. And this shows you the application of hydraulic systems like this. This could be used as a hydraulic lift system because you only need to apply a small amount of force in terms of the input in order to apply a larger force on the output. So you could actually lift a larger weight of object compared to the force you're applying here. Okay, so this is very, very useful in terms of hydraulic lift systems. And this principle states that a change in pressure applied to an enclosed fluid is transmitted undiminished. That means without being reduced. And it's transmitted undiminished to all portions of the liquid and to the walls of its container. Now, this is a very important principle. In order to understand that principle, let's just have a look at some very key terms. An enclosed fluid, well, this is a fluid which is isolated from the effects of external pressure. That means changing atmospheric pressure has no effect on that fluid because of the fact that it's enclosed. Bearing those 2 points in mind, let's have a look at this diagram here. We have a force acting on this piston, and this piston has a force F1. And the area of the piston is A1. And we have here, this blue section represents the hydraulic fluid. And we can see that the area of the piston on this side, on the right-hand side, is A2. And the force applied to that area, A2, gives a force of F2 acting in this direction. Pascal principle, we're going to apply that to the diagram we've just seen. And just to give you a little bit of information about the Pascal's principle, it was discovered by a Frenchman by the name of Blaise Pascal. And Pascal's law states, as we've mentioned before, that the pressure applied anywhere in a confined incompressible fluid is transmitted equally in all directions throughout the fluid. Now, let's apply some mathematics in relation to this principle. We have a force F1 acting on this piston. And what we can say is that the pressure exerted on that particular area of the hydraulic fluid is going to be equal to F1 divided by A1. Now, if you think about it in terms of the output force over here on the right-hand side, see that the pressure exerted on the area of this piston here is going to be equal to F2, which is the force generated, divided by A2, which is the area here. What is important to note is that we can rearrange this expression here, and we can write this as F2 is equal to P2 multiplied by A2, if we bring A2 over to this side here. Now, if you think in terms of what we have an expression where P2, the pressure exerted, is going to be the same as the pressure exerted over on the left-hand side in the fluid. In other words, P2 is equal to P1. So if we substitute in the value for P2 in terms of P1, in other words, P2 is equal to F1 over A1, we get an expression that F2 is equal to A2 divided by A1 multiplied by F1. And that's just by substituting in P2 for P1, which is F1 over A1. Now, the important thing to note is that the work done by the piston in moving from this position to, say, this position here, a distance of d1, that work done is going to be equal to the force applied multiplied by the distance. So F1 multiplied by d1 is equal to the work done in moving that piston from this position to that position. Now, the work done in moving that piston has to be equal to the work done in moving this piston. And we can work out what the work done is in terms of moving this piston is. It's going to be F2 multiplied by the distance moved by the piston, and let's call that d2. Therefore, we can rearrange this expression and we can say that d1 is equal to F2 divided by F1 multiplied by d2. Important to note is the following. Substitute in for F2 here. F2 is equal to A2 over A1 multiplied by F1. So that's A2 over A1 all multiplied by the force F1. If we substitute this value here for this value F2, what will happen is we'll get this particular expression because F1 will cancel. And we get that D1 is equal to A2 divided by A1 multiplied by D2. What we've effectively done is we've related the distance moved by the piston when a force F1 is applied to it. We're relating that distance to the distance moved by the other piston of the areas in contact with the hydraulic fluid. And this is an important expression, and we're going to have a look at this a bit later on in terms of the application of that expression, and also these expressions that we've also noted here. We're now going to have a look at a very important principle called the Archimedes principle. And this is very important when we consider forces in fluids. So what exactly is the Archimedes principle? Well, on the screen there is a statement or definition to help you understand the principle. The principle states that when an object is immersed wholly or partially in a fluid, the buoyant force of the fluid is equal to the weight of the displaced fluid. Now, in order to understand that, if we look at this diagram here on the left-hand side, this will hopefully make it a lot more clearer for you. When this particular object is lowered, and that's the yellow object, when that is lowered into a container which has water in it, what happens is, as that object is immersed into the water, it will displace water from that container. And the reason being is because a buoyant force will act on that object. And as a result of that buoyant force acting on that object, then what we have is a situation where the object itself will displace a certain amount of water, which is actually equivalent to the weight of the displaced fluid. So that water that's displaced is actually equivalent to the buoyant force. Now, to help you understand that in a bit more detail, let's just have a look at the animation again. So in the animation, you can see the object being lowered, and as the object is immersed in the liquid, it displaces liquid into the second beaker, which is at the side. And what we're basically saying, according to Archimedes' principle, is that the amount of liquid that's displaced, or fluid, is equal to the buoyant force acting on this particular object, which in this example is a metal. So for an object to float, the buoyant force must be greater than the gravitational force. In other words, this object, or this metal in this example, is experiencing a gravitational force of attraction which pulls it downwards. And so as long as the buoyant force, which is acting upwards, as long as that force is greater than the gravitational force, then the object is going to float, because the buoyant force is going to keep this object upwards. The net force acting on that metal, yellow metal, is going to be in the upward direction. So the object won't move downwards, it will actually float. According to Archimedes' principle, the buoyant force is equal to the weight of the water displaced by the object. And we'll have a look at this in a bit more detail as we go through this section. The diagram on the right hand side now just illustrates that last part in terms of the gravitational force and the buoyant force. Here you can see on the left hand side with the green object that the arrow for the buoyant force is greater than the arrow for the gravitational force. So you can see here that the green object is going to be able to float. And over here you can see that the gravitational force is greater than the buoyant force. So as a result of that, the object will begin to sink. And that's seen in the diagram with this red object, which is sinking into the fluid. Law of flotation basically is a very simple one, and it is this, that if the weight of the object is equal to the buoyant force of the fluid, then the object will float on the surface of the fluid. And we touched on that in the previous slide. So if we look at the diagram here, we can see that the buoyant force is acting upwards, and also the weight of the object is actually acting downwards. And because both of these are equal, then what we say is that we have an equilibrium set up in terms of the the net force is equal to 0. And so that means the object, in this case the duck, will just float. If the weight of the object is greater than the upthrust, then we saw that the object will sink, and we can see that again, just repeating what we've already seen in the previous slide, but just to make it very clear. Here you can see the object force, or the weight of the object, is greater than the buoyant force, so this object, this orange object, is going to sink. Here you can see the buoyant force is greater than the weight of the object, and so the object is going to float. Thrust is greater than the weight of the object. In fact, the object will move upwards. And we sometimes see this. For example, if you take a ball and you take a relatively big ball, a football, and you push it into the water, then because the buoyant force is greater than the weight of the ball or the weight of the object, sometimes the ball literally seems to project itself out of the water. In other words, the ball will move upwards when we try to push it into the water. Still problem, which is quite an interesting one because it gives you an understanding, hopefully, of the physics behind floating and sinking. I have two identical size cans of soft drink, and they're made by the same company. One of them is a diet drink and one is a regular drink. What do you think will happen when I place each of them in a container of water? What actually happens is as follows. We have Diet Coke and we have a ordinary regular Coca-Cola. The Diet Coke doesn't sink as deeply as the regular Coke. So why is that? Why is it that when we place a diet drink and a regular drink into a container of water, and both of them obviously have the same volume in terms of the container and are made of the same material, why is it that the Diet Coke tends to float to a greater extent? This is as follows. Same total volume. They're identical cans. However, in Diet Coke, what we have is artificial sweeteners, and these tend to weigh much less than sugar. So in the regular Coke, you have sugar, but the artificial sweetener weighs much less than the sugar. Both of these are in equal volumes. And remember, the sweetener used in diet drinks is much less in volume than the amount of sugar which is used in regular drinks. Therefore, based on those two pieces of information, we can say that the diet drinks, they tend to be less dense, and as a result of that, they tend to be more buoyant than regular drinks. And that's the reason why diet drinks tend to float when you place a diet drink and a regular drink at the same time in water.